Hello, so this video involves some solutions to problems from the MS practice exam for midterm 3. So the images below represent three-dimensional slices through different solids. Which one represents the one with the highest melting point? So we have plus 3 minus 2, plus 2 minus 2, and then this would be interpreted as like a molecular solid, some sort of molecular compound, because there's no charges at all. Maybe this is something like 2 fluorine atoms or 2 chlorine atoms, not expected to have a very high melting point without charges. So we're choosing really just between 1 and 3. We can roll 2 out as having a high melting point. And so compound 1 is going to end up having the higher melting point simply due to the plus 3 cation having a greater charge than the plus 2. So melting point here is generally proportional just to lattice energy. The higher the lattice energy, the higher the melting point. So this problem here gives us a Born-Haber cycle. So I usually think of starting a Born-Haber cycle right here, or even right here. So the way we generally would work these problems out in class would be you take the calcium chloride solid, convert them into their elements. That's the opposite of the enthalpy of formation of calcium chloride. And then from there, we would take solid to gas for the metal. And then from there, we would break the bond in the nonmetal. And then from there, we would ionize the metal. That takes more energy. So it takes energy to convert an ionic compound back into its elements. It takes energy to convert solid metal into its gaseous metal for it to sublime. It takes energy to break the bond in the nonmetal. It takes energy to ionize an electron off calcium. It takes even more energy to ionize the second electron off calcium. And then we get a little bit of energy back when we take the electrons from calcium that lost and add them to chlorine to make Cl-. So Cl- has a slight negative electron affinity, so we get a drop in energy. And then once we form Ca2+, Cl-, then we get the electrostatic attraction. The electrostatic attraction of those ions together is what defines the lattice energy. So the lattice energy drops down and becomes a stabilizing factor. So to separate the compound, to separate the ionic compound, to go uphill here corresponds to the plus lattice energy. And once you make the ions and they experience their attraction together, then that's the negative lattice energy. That's the dropping in energy due to the attraction of the ions. So when we look at the question, which steps in the Born-Haber cycle for calcium chloride are exothermic, we're looking at this diagram above and just assessing that delta H1 is written as a negative number, delta H6 is negative, as well as delta H7. So we're just looking at this diagram here. We're not really thinking of the steps we might write to actually solve and determine the lattice energy for calcium chloride. Determining the lattice energy would be figuring out a way to determine what the magnitude of delta H7 is equal to. And we've done that problem a few times, and we'll see one more attempt here in a moment. But for this problem here, we're just trying to figure out which of these values in this diagram refer to negative quantities. So it's delta H1, 6, and 7. So then looking at this diagram here, which step in the diagram refers to the second ionization energy of calcium? So the second ionization energy of calcium would be this number right here. And so the first ionization of calcium is 590 kJs, the second is 1145, and that's delta H5. So we'll be looking at delta H5. So again, using the diagram, can we calculate the lattice energy of calcium chloride? And so if we want to determine what delta H7 is, what we might do is say, well, what are all these numbers here added together? And so if we see how this diagram here from calcium chloride being formed from calcium and chloride is minus 795, we need to calculate the energy it takes to get up to here from calcium chloride. So that would be plus 795. Then we'd add 178, then 242, then 590, then 1145, and then we subtract 698. So we're taking plus 795, plus 178, plus 242, plus 590, plus 1145. So we're taking the energy it takes to go from calcium chloride to its elements, the energy it takes to take calcium solid to gas, energy it takes to break the chlorine bond, i.e. 1, and IE2. So this is IE2, IE1, the bond energy of chlorine, the bond association energy of Cl2. This is the delta H of sublimation of calcium solid, or it's the enthalpy of formation, if you will, of calcium gas. And then this is the minus delta HF of calcium chloride. And then lastly, we're going to subtract the electron affinity. So we're going to subtract 698 due to the electron affinity of chlorine, which is a negative number. We're taking into account how there's 2 moles of chlorine undergoing that step. The electron affinity of chlorine is about half of 698, and it's negative. And so the electron's more stable, added on to the chlorine into the chlorine shell. So we do all this arithmetic, it should work out to answer B. So number 13, what happens when 2 hydrogen atoms form a molecule of H2? A bond forms once the 2 hydrogen atoms reach a distance that is most stable. A process which requires energy is choice A. Now, the requiring energy part is the part that sounds wrong to me at first. So when we're thinking of 2 H atoms forming a bond together, they will reach a stable bond at about 0.74 angstrom, and energy should be released. So the hydrogen molecule becomes more stable because it contains more energy than 2 non-interacting H atoms. It does not contain more energy. The potential energy is dropping when we make the bond. So the energy is actually reducing. The potential energy of the system, that would be the molecule, decreases, making the system, the molecule, more stable. So the 2 H atoms are more stable as a molecule than they were separated. That is true. So that sounds correct. Let's just make sure D is incorrect. The pair of electrons make a single rigid bond, forming a stable connection between the 2 H atoms, like a stick joining the atoms together. Okay, the pair of electrons make a single rigid bond, forming a stable connection between the 2 hydrogen atoms, like a stick joining the atoms together. That's an interesting choice. I suppose the part that makes it wrong, as we think about this, is just the word rigid. That the H bond wouldn't be like a static bond where it would never break or the bond couldn't stretch. There would be some natural stretching frequency of this molecule, so it's not always going to be exactly that ideal bond distance, like we said, of about 0.74 angstrom. It's going to be a flexible bond, like most molecules do vibrate and don't stick at that magic bond angle exactly. So there's some small potential energy for the molecule to be stretching. So I think that's what makes choice D incorrect. Sounds pretty close to right, but it's just that one, the rigid bond, I don't quite know what to make of that statement. So a bond really isn't at all like a stick joining the atoms together. It's just the sharing of electrons among the atoms, making the molecule more stable than the separated atoms. So when comparing a carbon-carbon double bond and a carbon-carbon triple bond, the double bond, so we have like something like this, we have 6 bonding electrons versus 4. So this bond with the triple bond should be shorter. The double bond should be longer. And the shorter bond should be stronger due to greater electron pairs holding the atoms together. And the double bond will be weaker. Okay, so when comparing a double bond to a triple bond, the double bond is longer and weaker. So it should be choice D. Okay, we can also think of potential energy diagrams. Like if we were to compare and say, okay, we have H plus H, but what about C plus C to make a double bond compared to the H bond? Well, the double bond is stronger, and it actually ends up being a little bit longer than the hydrogen bond. So we'd see a potential diagram that might look something like this for the carbon-carbon double bond forming. So this would be the CC double bond. And so then if the carbon-carbon triple bond is stronger than the carbon-carbon, and it's also shorter, then it should look something like this. And so it's going to have a larger drop in energy compared to the double bond. And we showed this in class a couple times before when we were thinking about bond strengths. And so it's this energy here minus this that would be indicative of that triple bond strength. I think it was, I don't remember the number off the top of my head, but it's around 1,000 kJs per mole. The double bond's around 600 kJs per mole. So a lot stronger in terms of the triple bond. It's also shorter. All right, 3 isomers of C2H2Cl2 are shown below. I think we were actually just talking about this in lecture on Thursday. But we have the chlorine dipoles pointing away, so we get this big negative charge on one end of the molecule, not opposed on the opposite end. Likewise here, dipoles oppose each other exactly opposite each other. So that makes 2 nonpolar. 3 has the 2 dipoles this way, so we get this big negative charge on this side of the molecule, nothing exactly opposing it on the opposite side. So if we also had a molecule with chlorines in every spot, then this molecule would also be nonpolar. So only 2 here, only molecule 2 is nonpolar. The other 2, 1 and 3, would be polar. So to assess a molecule as being nonpolar, we want to have the exact same atom opposing each other in the molecule. So we have 2 hydrogens opposing each other, 2 chlorines opposing each other. There was an example at some point in the homework of a platinum compound that forms a square planar complex where you can have 2 chlorines and 2 ammonia molecules on this platinum. So this molecule here would be polar, and then if you were to put the 2 chlorines exactly opposing each other, 2 NH3s exactly opposing each other, then this molecule here ends up being nonpolar. I don't remember which one. One of these is actually an anti-cancer drug, and the other one is actually poisonous. So they have much different properties as a basis of their difference in polarity. So 18, delocalized electrons are electrons that are spread over a number of atoms in a molecule using unhybridized p orbitals rather than localized electrons, which are electrons located between a pair of atoms. So likely we get that defined for us here. Sometimes you may see this question not actually giving that type of definition. And so let me erase this. I might need some space to write here. But so then the delocalized electrons, or the bonding in which molecule below, is best described with delocalized electrons. So we have nitrate, CCl4, SO4 2-, and formaldehyde. So let's start with formaldehyde. So we have HCH, double bond O, lone pairs on the oxygen for our best Lewis structure. This is a classic case of a localized bond. So this double bond is exactly between the C and the O. So we'd have a leftover p orbital making the pi bond. So we'd have 1 pi bond between the C and the O. If we look at CCl4, we don't have any unhybridized. We have an sp3 molecule for trigonal planar, or for tetrahedral. Same thing for SO4. So neither one of those have any leftover p orbitals to serve a model with delocalized electrons within them. Now nitrate will be the one that can have delocalized bonding. Let's draw the molecule this way. Trigonal planar, roughly, and actually exactly 120-degree bond angles. We may draw a Lewis structure that looks like this. And if we do, we'd have a plus formal charge on nitrogen, minus on the 2 O's. But we don't actually end up with this localized bond here. We actually don't end up with this localized double bond between that N and the O. Instead, if you picture this oxygen having the same resonance, then it would have an O orbital sticking straight up, as would this O, and then we get simultaneous overlap with all those orbitals simultaneously. So the real structure of N, O3-, of course we've done this a few times, but would look something like this, where the bonds could be described as being of an order of about 4/3. So we got 4 pairs of electrons spreading across the 3 covalent bonds, and the charges on the O's end up being about -2/3 in terms of a formal charge. So we have a formal charge on each of the O's is either -1 in one of the possible resonance structures, -1 in the other, and 0 in the third. So you just average out the 3 possible charges on the O's, average it out to -2/3 for each of them. So that makes the total charge on all the O's work out to be -2, and then we have a plus formal charge on N, balancing out to give the overall minus charge. Now this is the classic case, so we don't need to necessarily picture all this to answer this question, but it maybe helps us understand what nitrate looks like. 3 equivalent NO bond links in the molecule, 3 equivalently charged oxygen atoms, because we don't have localized bonding in this molecule. We have delocalized bonding, where that double bond spreads itself out at all times across the whole molecule. So to answer the question, the bonding in nitrate would be best described with delocalized electrons. draw the phosphate ion based on formal charge rules and determine the formal charge on the phosphorus atom. So we've had this issue with molecules like sulfate and phosphate. How do we sketch these molecules? So we go PO4, single bond, the oxygens, like we've done a bunch of times before, complete their octets, counter electrons. We have 5 plus 4 times 6 plus 3, 32 electrons. That's how many I've distributed in my Lewis structure. Issue might be, though, that we have minus formal charges around the molecule, and then we have a plus 1 formal charge on phosphorus. So if we're told, like in this problem, to use the formal charge rule, then we make a double bond. So we have a P double bond O, 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 minus formal charges all the way around the oxygens, and then just 2 lone pairs on the one oxygen. So the formal charge here on this phosphorus would be 0. Okay, so this would be the Lewis structure of phosphate that follows the formal charge rule. Now, we'd have to imagine some type of resonance occurring to make all of these oxygens the exact same length. So the bond order here would be 1, 2, 3, 4, 5 bonding pairs of electrons spread across the 4 bonds. So this would be like a 5/4 bond for each of the phosphorus atoms, or for the phosphorus oxygen covalent bonds. And then all the charges on the O's would either be -1, -1, -1, or 0. So you'd have -1, plus -1, plus -1, plus 0, divided by the 4 possibilities for each of the O's having a charge perhaps best described as being minus 0.75. Now, the only minor issue here, though, from hybrid theory and the picture of delocalized bonding that we were just talking about with nitrate, is that there's actually no way to actually see what this resonance overlap might look like. So there would not be delocalized bonding occurring within the standard picture that we see for things like nitrate, for carbonate, for benzene, because we don't have a planar molecule with leftover p orbitals to serve as a nice picture to actually see what the orbitals might look like to allow this resonance. Now, this would be a really good reason why this structure is probably wrong, but again, our book is a bit weak on this topic and doesn't seem to want to make a compelling case for the formal charge rule, likely a rule not worth following in molecules like this. So the simple thing to know for the exam is if we say, well, you can give a Lewis structure for one that follows the octet rule, or one that follows the formal charge rule, and you can work out formal charges and answer questions very simply. And then perhaps in the back of your mind know that maybe the octet rule structure makes just a tad bit more sense. So then number 20 is a question that honestly I'd be really upset if we don't all get this type of question right on the exam, because we've seen this in chapter 5, we've seen it in chapter 8, we've done examples in this class so many times before. The big idea here is that the delta H is an approximation of so it's an approximate value that we get from taking the bond strengths of the reactants, added together. I think technically I have it backwards. So it's just the sum of the bond strengths of the reactants minus the sum of the bond strengths of the products. What am I doing here? Let me erase. So it's the sum of the bond enthalpies, symbol D for the reactants, minus the sum of the bond strengths of the products. Now the new thing here is maybe you'll have to actually sketch a Lewis structure to know the type of bonding in the molecule. So for like N2H4, the slight bit of issue in this problem might be that we would need to have the 2 nitrogens bonded together, 2 hydrogens, and then lone pairs on the N. That gives us the right number of electrons, 2, 4, 6, 8, 10, 12, 14, for 10 plus 4 for 14. Chlorine single bonded, NH2Cl, and HCl. So single bonds the whole way around the molecule. We have to take into account we have 2 of these, so we just have to very carefully count our bonds. So we're breaking the bonds of 1 NN bond, so 163 kJs. We're breaking 4 NH bonds, so that's 391. And then we're breaking 1 chlorine bond. That's that's 242. And then we are making bonds. We're making 2 NH bonds times 2. So we're making 391 kJs times 4. Now notice that these do cancel each other out. You can either neglect that, like you could truly only take the reactance bonds that are actually broken and perhaps neglect the bonds that are still there in the products, or you can just break them all and then make them all. Don't overthink these problems or don't underthink these problems. And so then we're making 2 NCl bonds. So the NCl bond, well, that's pretty strong, 615 kJs times 2 of them. So we just have to take into account stoichiometry and the number of each of these bonds. So 1 NN bond, 163 plus 242 minus 615 times 2. So that's looking probably like answer D. What is the molecular geometry name of BRF5? So BRF5, central bromine, 7 for each, 42 electrons. So fluorine, 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 and then a lone pair on bromine. Okay, and so we get the lone pair on bromine because each F has 8 electrons. I'm not going to draw all those in. So we have 40 electrons from the 5 fluorine atoms, that's 2 electrons left over, that go onto the central atom. So I have 1, 2, 3, 4, 5, 6 total domains. One of them's non-bonding, and so that should take the general structure of a square pyramid. So I get a square pyramidal structure. The molecular geometry names, you should be able to sketch the shape, and you should be able to look at the shape and interpret what name or shape best describes the figure. So the molecular geometry just takes the atom's position in the molecule, the shape that describes where the atoms are. Of course, those atom shapes are determined by all of the electron domains. Drawing below shows the overlap between 2 hybrid orbitals to form a bond on a hydrocarbon. Which of the following could identify the hydrocarbon? This is trying to show us that we have an sp2 and an sp2 center. And actually, I think the next question after this one is, what type of overlap is this? Well, it's sp2, sp2. sp would look just like this. We'd have the 2 orbitals 180 relative to each other. So this would be sp We could have sp overlap with like sp2. We could have sp3 overlap, or we can have sp3. And I guess that would be it. So sp3 overlap. We oddly couldn't have. Could we have sp3 overlap? I guess we could. So you can have all of the hybrid orbitals overlap with each other. And so CH4 doesn't make any sense because we're not going to get sp2 overlap. We're going to get sp3 for the tetrahedral carbon overlapping with 1s. C2H6 is going to be 2 tetrahedral carbons, so that would be sp3 overlap for the 2 carbons. C2H4 is the right answer for the question because we will have 2 trigonal planar carbons adjacent to each other, so they'll have sp2 overlap for the carbon atoms. So that's looking like the overlap of the 2 carbon atoms in ethylene. Acetylene doesn't make any sense because that one would be the sp-sp overlap for the 2 linear molecules. So the answer here would be C. Number 28. Here, select the atom and the molecule with this set of hybrid orbitals. Note the lone pairs of the molecule are not shown in the diagram. What that means is that this oxygen really has 2 lone pairs of electrons. I mentioned in class that I actually don't find these diagrams to be all that valuable because they're kind of, in my opinion, a little bit silly. Because what this type of diagram is trying to suggest is if you look at, say, atom 1, that maybe carbon hybridizes and then bonds with hydrogen. I think that's wrong. I think we're trying to look at a molecule that exists and try to describe the bonds in the molecule. What this picture is trying to suggest is that the atoms hybridize and then go looking for atoms to pair up with. That's not really what hybrid theory is actually trying to describe. And I think it kind of blurs the picture that we're just trying to come up with a bonding model for these molecules once they exist and once they adopt the geometries that we know them to adopt. So in a way, I think these diagrams are kind of silly. But for atom 1, What this diagram might look like using this approach would be that we should have sp3 for 1. So 1 would be wrong. 1 should look like sp3 for the carbon. So 4 orbitals that are all sp3. And then we should have 1 electron in each of those because carbon has 4 valence electrons. And then it should have 2 electrons in its core 1s orbital. And so this should be what atom 1 looks like. Let's do atom 3 next. So atom 3 should have 2 lone pairs. So oxygen has 6 valence electrons, so it should have 2 electrons and a 1s. And then we would describe that oxygen as also being sp3. So we'd have 3 sp3s, except we'd have 2 pairs of electrons in those sp3 orbitals. So we'd have those 2 electrons here, then we'd have 1 electron from O in each of the other sp3 bonds. So we'd have like 1 dot here, 1 dot here, lone pair, all of these in sp3 orbitals. So all those being sp3 because oxygen has 4 total domains. So then likewise, if we look at this oxygen here and say what should 4 look like, so that's 3 above. 4 should look like, again, a 1s with 2 electrons, and then we should have an sp2, that's only 3 orbitals. So 3 atomic orbitals make 3 new hybrid orbitals. So we're going to get, whoa, why did that happen? So then we're going to get 2 pairs of electron and 2 of the sp orbitals, so those would be these electrons, and then 1 extra electron in an sp orbital. And then we'll have 1 electron left over in a p orbital. And so this leftover electron in a p orbital will pair up and make the pi bond with carbon, and then this will make the sigma bond with carbon. And so we're just kind of looking at this O and kind of saying, okay, O here would have electron pair here, electron pair here, electron here, and then in an orbital sticking straight out, it'll have 1 electron in that orbital as well to make a pi bond. And so finally, this diagram here would best describe atom 2. Why atom 2? Because there's 4 valence electrons that matches a count for carbon. So we'd have an sp2, carbon, trigonal planar, so 3 electrons in the sp2 hybrid orbitals, and the last one in the p orbital. So, and again, we could make one of these overlap with the sp3 carbon that's adjacent. We can have one overlap with the O sp3 that's adjacent, and the other one overlap with the sp2O of the double bond. And then the p orbital goes with the p orbital of the sp2O. Okay, so the slide's pretty messy, but I think if we boil this down, let me actually add a slide. So if we think of this carbon here, what we're kind of saying is have electron, electron, electron here, here, and here in sp2 orbitals, and then it'll have this extra orbital sticking straight up with an electron in that one. If we maybe think of this diagram in a slightly different way here, where maybe we can draw this O coming out, this O going, or this sp2 coming out, this one coming back, then maybe we can think of this dot here. So we'll have O pair up here, here and here, with 2 electrons in each of those orbitals for its lone pairs, and then 1 electron here. So we make a pi bond here, so this is 1 pi, and then we get our sigma here. So this is just one type of diagram or method to help us understand the bonding of these molecules. You know, I think a better question is just looking at things like this and counting 1, 2, 3, 4, 5, 6, 7 sigma total plus 1 pi. Or counting that we have 4 lone pairs also on this molecule, describing this double bond here as a sigma and a pi, describing this O as sp3, this is sp2, this is sp3, this is perhaps best described as sp2, describing those sort of things, describing bond angles is more the point. These diagrams here can help us get to the sp2 or picturing the types of overlaps that are made in this type of molecule. Okay, the last question for this video would be this one here. So let's apply and use the MO diagram. I had to cut off the question just to get this to fit in on a nice slide page. But these are the diagrams. You'll find these at the top of your test near the periodic table. Applying this diagram here, which of the following has the longest bond length? So this type of question here is just trying to get us to think of bond order. So the molecule with the smallest bond order should be the longest bond. Molecule with the biggest bond order has the greatest number of bonding electrons and hence would have the shortest bond. So N2 plus, we just got to go to the right diagram. So N2 plus would look like that one, 8 total electrons in terms of the valence count. So 2s, 2s, 2p, 2p. And the electrons going in, sigma 2s, the antibonding go up, pi 2p, sigma 2p, pi star 2p, sigma star 2p. We can get a bond order out. We have a total of 6 bonding electrons minus 2 antibonding times a half. So our bond order for N2 plus would work out to be equal to 2. So that would be describing a double bond between the two nitrogens if the molecule has a net charge of plus 2. If we have F2 or 2 fluorines with a peculiar count of a minus charge, so F2 minus would be the total of 7 plus 1 for 15 electrons. So we'd be putting 2, 4, 6, 8, 10, 12, 14, 15. So we have a total of 8 bonding electrons. That's the most bonding electrons we can have in an MO diagram for something like a second row molecule. Minus 7 antibonding electrons times a half gives us a half for our bond order. O2 with a minus charge would be with this base diagram here. So O2 minus, let's do that in red. So O2 minus would only have a total of 6 plus 1 for 13 electrons. So we got to kick 2 out. So let's get rid of that one and that one. Oh, yeah. And so that's maybe I'm missing my drawing. So we'll kick out one of those. So we'll still have an odd electron count. So we have a total now of 8 bonding electrons, 5 anti-bonding electrons, times a half for our bond order for a 3/2 bond. O2, we kick out the last electron here from this structure. So O2 will have 6 plus 6 for 12 electrons. And so then that would have a bond order of 2. So our O2 bond order would be 8 minus 4. And I do realize I skipped N2 minus. So that was O2. That was F2 minus. This is O2. 8 times 4 times a half would be 2. N2 minus will have a bond order. It will look like the N2 plus an electron. So it'll have a bond order that actually looks just like O2 minus is. So it'll have 8 bonding electrons. Or no, excuse me, it won't have the same bond order as O2 minus. So I'll have 8 bonding electrons minus 3 anti-bonding electrons times a half for a 5/2 bond. So of these, N2 minus will have the shortest bond because it has the greatest bond order. And the longest bond will be the bond order of 1/2, which is F2 with a minus charge. So F2 with a minus charge will have the longest overall bond due to having the shortest bond order. So if we ever find that we have 2 molecules with the same bond order, then we'd be comparing which atom is bigger versus smaller. So let's say we were comparing, we did that one in class. But let's say we were doing a slightly different problem, and we were comparing something like, I don't know a good example. We'll just say it simply like this. If you're comparing 2 single bonds, you would choose the single bond with the bigger atom to be the longer bond. So hopefully we can go through label diagrams, think about how sigma bonds should look like this type of bonding if it's s orbitals, this type of bonding if it's p orbitals. So we're making our bond in the middle, so our greatest electron density is in the middle. So if we then have our nuclei with the greater density over here, that's kind of what our anti-bonding sigma orbitals look like. And so if you see something that looks like this, then it's the sigma p orbitals where you can kind of see the p shape orbital still. But if it's just symmetrical like this, where it's kind of shaded outward like this, then that's the sigma 2s star. And then our pi orbitals look like the pi electrons here. This makes one pi bond. The other pi bond would be the p orbitals then sticking straight out of the page, doing the exact same type of thing. And then the anti-bonding p orbitals look like where the electrons kind of look like a butterfly, if you will, because our density is greatest away from the molecule, from where the nuclei are. So hopefully we can picture orbitals, we can sketch orbitals, label them, we can fill electrons in, get bond orders, we haven't talked here today in this video, but we can discuss which of these molecules would be, say, paramagnetic. Paramagnetic have unpaired electrons. So N2, if we're saying which are paramagnetic, N2 plus would not be paramagnetic. F2 minus would be paramagnetic, has one unpaired electron. O2 minus has an unpaired electron, would be paramagnetic. Anything here with an odd count has to be paramagnetic. N2 minus would be paramagnetic, and O2 is our classic example of a paramagnetic molecule. So all but one of these molecules would be paramagnetic and hence drawn into a magnetic field. N2 plus would actually be weakly repelled by a magnetic field. Okay, so this was some select problems to review from Dr. Foos's, from his practice midterm that's posted up on Carmen. That's all for today, or at least all for this video.